There are many processes that we come across while dealing with thermodynamics, but out of those processes, isothermal and adiabatic processes are of such types that you come across them many times. First of all, we are going to discuss isothermal process at length. Isothermal, I told you, T remains constant. Now, in order to maintain the temperature constant, obviously the heat exchange should immediately leak through. Means whatever the heat has been transferred to the system should immediately go out of the system, and this could be possible only when the thermal, that container that we have used for the process, must be a perfect conductor. Only then it will allow the heat immediately to go out. That means first condition you get that for isothermal process the container should be perfect conductor, or the other process is that your process that you are adopting is very slow, extremely slow, so that whatever the amount you are transferring, that will gradually leak through, that will having sufficient time to leak through. So if the process is very slow, it means the clear hint is that for isothermal process. So in numerical problems, you see, you are told, you are informed regarding isothermal by different ways, by different indications. One, you got that process is in perfect conductor, and the other is that process is it's damn slow. Now, if you plot the graph, you see at constant temperature, Boyle's law, that is P proportional to 1 upon B. If you plot a graph between P and B, it's going to be a rectangular hyperbola, and this is named as isothermal curve. If we plot a curve between P and B at constant temperature, it will be known as isothermal curve. One very interesting result we have for these isothermal curves, you see, I am going to plot two curves, T1 and T2, and suppose I draw one particular line. You see, this line is at constant pressure. Isothermal curve means throughout the curve the temperature will remain constant. So this is the curve at T1 and this one is the curve at T2 temperature. The entire curve is at T2 temperature. At this very juncture, suppose the volume is V1 and at this juncture this is V2, you could apply the relation PV equal to RT1. For the same gas having 1 mole, we are plotting, we have plotted the two curves and we are using this equation. For this, you see, point, say, B, we are writing PV1 equal to RT1. And for this, we are writing, for this point C, PV2 equal to RT2. If you take the ratio V1 upon V2, this is going to be T1 upon T2. But since from the graph itself it's clear V2 is greater than V1, obviously T2 will be greater than T1. Here V2 is greater than V2. You see, with V1 it is, with V1 it is T2, and with V2 it is T1. If you take the ratio, it's going to be T2 upon T1, T2 upon T1, and here since V2 is greater than V1, T2 is going to be less than T1. Finally, you got the result that in these two curves, T1 is greater than T2. It's a very important result that whenever the isothermal curve is at a greater distance from the origin, temperature will certainly be greater. So you have to remember this important point, that out of many isothermal curves, the curve that is at furthest distance from the origin will be corresponding to maximum temperature. Then we have plotted two curves here for expansion and compression. This is for isothermal expansion, in which the volume regularly goes on increasing, and this is that for compression, the volume is regularly decreasing. But isothermal is still isothermal. Expansion and compression means you have simply reversed the direction. Curve will remain same.